There's a word you've heard 100 times and probably never stopped to feel the weight of it. Space-time. Einstein's space-time. The fabric of space-time. Space-time is curved. Scientists say this so naturally that it's misleading. Because when you really stop to ask what space-time is, not what it does, but what it is, you discover something a bit uncomfortable. Nobody knows. You use this idea every day. Your GPS wouldn't work without it. They've already photographed it bending around a black hole. They've already detected ripples passing through it. And even so, there isn't a ready answer for what it's made of. I'm going to show you why this is one of the biggest gaps in physics, and why closing that gap could turn everything you think you know about the universe upside down. This starts in 1905 with a 26-year-old office worker at the patent office in Bern, Switzerland. He wasn't a professor. He didn't have a position at any university. He spent his days examining patent applications for electrical devices and at night thinking about physics. That's all. No one was asking for it. No one was paying for it. His name was Albert Einstein. And in that single year, he published 4 papers that would change physics forever. He proved that atoms were real based on the erratic movement of particles in water. Another helped to found quantum mechanics. And 2 of them introduced what we now call special relativity. Special relativity seems complicated, but the central idea is straightforward. Einstein realized that the speed of light is always the same, no matter how fast you're moving. If you're on a train going 100 km/h and you throw a ball forward at 20 km/h, someone standing on the ground sees the ball at 120 km/h. The speeds add up. That's what we expect. But light doesn't work that way. On a spaceship, at half the speed of light, if you shine a flashlight ahead, you'd expect it to go 1.5 times faster. From the point of view of someone observing from outside, that's not what happens. Light travels at about 300,000 kilometers per second. Both for you and for someone observing from outside, the same speed always. Einstein's answer to this dilemma was radical. Space and time adjust themselves to keep the speed of light constant. If you move very fast, time passes more slowly for you from the point of view of someone standing still, and the distances in the direction of your movement actually contract. These aren't optical illusions. They're real physical effects. Time and space are not absolute, they are relative. The only absolute thing is the speed of light. That overturns centuries of assumptions. Newton had built all of physics on the idea that a second is a second, no matter where you are. Einstein showed that it's not. Time is flexible. Space is flexible. Think about what that means. On a ship traveling at 99% of the speed of light, on a journey to a star 10 light years away and back, for you on board, only a few years would have passed. But upon returning to Earth, 20 years would have passed here. Your friends would be 20 years older. This is not fiction. It has already been confirmed repeatedly. Unstable particles and accelerators live much longer when traveling at 99.9% of the speed of light. Atomic clocks flown around the world show, upon return, that less time has passed on them than on an identical clock that stayed still. A difference of a few hundred nanoseconds, but measurable and exact. The implications are profound. There is no universal now, no cosmic clock ticking the same everywhere. Different observers, moving at different speeds, would disagree about which events are simultaneous. Time is not a river flowing at a constant rate. It's more like a fabric that stretches and compresses depending on how you move through it. But Einstein wasn't finished. Special relativity only dealt with constant speeds, not with acceleration nor with gravity. And gravity was a problem. Newton's law had worked brilliantly for 200 years, but it acted instantaneously. If the sun disappeared right now, according to Newton, the gravitational attraction would vanish instantly across 150 million kilometers of empty space. But Einstein had just shown that nothing travels faster than light, and sunlight takes about 8 minutes to get here. Gravity couldn't act any faster than that either. There had to be a delay. Something needed to carry the gravitational force without exceeding the speed of light. This led Einstein to some of the most productive thoughts of his life, what he himself called the happiest thought of his life. It came to his mind in 1907 at the patent office, when he imagined a worker falling from a roof. While falling, he doesn't feel his own weight, he's in free fall. If he let go of the hammer would float next to him, without seeming to accelerate in any direction. It seems obvious today, after so many images of astronauts floating on the International Space Station. But Einstein realized something profound. The falling worker and the floating astronaut experience exactly the same thing. The astronaut is not in zero gravity. He is falling toward Earth, but he's moving too fast sideways to actually hit the planet. He is in orbit, continuously falling, continuously missing the ground. Being in free fall is indistinguishable from being in empty space, with no gravity at all. And being in a rocket accelerating upwards is indistinguishable from standing still on the surface of a planet, feeling gravity pulling you down. In a closed room with no windows, no experiment can tell the difference between the two situations. The effects are identical, and this is the equivalence principle. Acceleration and gravity are the same thing. And this was the key insight that led Einstein to general relativity. If acceleration affects space and time, and gravity is equivalent to acceleration, then gravity also needs to curve space-time. It took another 8 years to solve the math. From 1907 to 1915, Einstein struggled with the equations and learned tensor calculus, which he had never studied before, with the help of his mathematician friend, Marcel Grossman. He made mistakes, published wrong results, corrected them, and tried again. He himself later said that the last year, from the end of 1914 to November 1915, was the most exhausting period of his entire career. At one point, he thought he had the right equations. He published them and realized they didn't reduce to Newton's law in the correct limit, a warning sign that sent him back to the drawing board. The breakthrough came in November 1915 in Berlin, during a series of lectures at the Prussian Academy of Sciences. On the 25th of that month, Einstein presented the final form of the field equations, 10 interrelated equations describing how the curvature of space-time is determined by the distribution of mass and energy, written in a compact form as G equals 8 pi t. They seem simple, but solving them for real situations is extraordinarily difficult. They are nonlinear. Curvature influences mass and energy, and they also affect curvature. Even today, solving them for two colliding black holes requires supercomputers running for weeks. The classic analogy to visualize this is a stretched rubber sheet. A heavy ball in the middle creates a depression, and a smaller ball rolling nearby curves toward it. Not because it's being pulled, but because the sheet itself is curved. That's what mass does to space-time. The sun curves it, and the Earth, trying to move in a straight line, is forced to follow a curved path. This curve is the orbit. We experience this as gravity, but for Einstein there is no pull at all, just the Earth moving through curved space-time. The analogy helps, but it is misleading in one aspect. The sheet is two-dimensional, curving in 3 dimensions, while space-time, with its 4 dimensions, curves upon itself. It's hard to visualize since our brains evolved for 3 spatial dimensions, not 4. Objects follow geodesics, the straightest possible paths through the curvature. One of the first successes was to explain Mercury's orbit with a slight precession that Newton couldn't account for. Einstein's equations predicted the exact amount without needing a hidden extra planet. Space-time was just curved more strongly near the sun. The real test came in 1919. The theory predicted that light would be bent by the gravity of the sun, visible only during a total eclipse. On May 29, 2 expeditions, one to Principe Island in Africa, led by Arthur Eddington, and another to Sobral in Brazil, they photographed stars during the eclipse and compared them with nighttime photos of the same stars without the sun nearby. The stars had shifted exactly as predicted. Announced in November 1919, the result turned Einstein into a celebrity. Overnight, headlines all around the world. By around 1922, all of physics agreed. Einstein had solved gravity. The problem was settled. But it wasn't. The equations were beautiful, but hard to work with, and most physicists at the time could only solve them in simple cases. One of the simplest solutions came from Carl Schwarzschild in 1916, just a few months after Einstein's publication. A German physicist serving in World War I, even on the Russian front, found time to solve the equations for the simplest possible case: a spherical mass without rotation, alone in a vacuum. The solution worked, but he noticed something strange. At a certain distance from the center of the mass, the equations gave infinite values. This distance became known as the Schwarzschild radius, about 3 kilometers for the Sun and 9 mm for the Earth. A number that seems meaningless since the Sun has a real radius of 700,000 kilometers. Most people treated that as a very strange topic. Schwarzschild died a few months later, at the age of 42, on the Eastern Front, without knowing how important his solution would become. For decades, the Schwarzschild radius remained a curiosity. Einstein hated the implications. Compressing a mass within its own Schwarzschild radius would make space-time curve so strongly that not even light could escape. A black hole with a singularity at the center, where the curvature would become infinite and the laws of physics would break down. Einstein thought this was absurd, a limitation of the theory, not a real prediction. He wrote articles in the 1930s arguing that some force would always prevent collapse beyond that radius, such as electron or neutron degeneracy pressure. Something about that moves me. The man who discovered that space-time curves was the same one who spent decades refusing to believe in one of the most direct consequences of his own discovery. But in 1939, J. Robert Oppenheimer, who would later lead the Manhattan Project, and his student Hartland Snyder, published a paper that changed everything. They mathematically modeled a massive star running out of fuel and showed that nothing could prevent its collapse. The star would shrink beyond the Schwarzschild radius until it became a singularity. Later studies confirm this even for realistic models. There is a mass limit beyond which no known force can prevent collapse into a black hole. The term was only coined in 1967 by John Wheeler, who had been tediously repeating the phrase, completely gravitationally collapsed object, during a lecture in New York, until someone shouted from the audience, "How about black hole?" Wheeler adopted the name on the spot. Einstein hated the result, but he couldn't find any flaw in the math. He died in 1955 without ever accepting that black holes were real. For the next decade, most physicists remained skeptical, but observations began to accumulate. In the 1960s, astronomers discovered quasars, extremely bright objects pouring out enormous amounts of energy from small regions. The only plausible explanation was supermassive black holes feeding on gas and dust. In 1965, objects became of great importance. Once a star collapses beyond a certain point, the formation of a singularity is mathematically inevitable. It's not a matter of the star being perfectly spherical, it's an unavoidable consequence of the very laws of general relativity. In 2020, the Royal Swedish Academy of Sciences recognized this entire line of work at once. Half of the Nobel Prize in Physics that year went to Penrose, precisely for this theorem from 1965. The other half was split between Reinhard Genzel and Andrea Ghez, who spent almost 3 decades tracking, with increasingly precise telescopes, the orbits of stars revolving around an invisible object at the center of our galaxy, proving in practice that only a supermassive black hole could explain that movement. It was the first time the Nobel Prize in Physics recognized a theoretical result based entirely on general relativity, more than 100 years after it was published. Stephen Hawking extended this work in the late 1960s and early 1970s, together with Penrose and others. He proved that singularities are generic features of general relativity and do not appear only in black holes. The Big Bang itself was a singularity. By running the expansion of the universe backwards with Einstein's equations, you inevitably arrive at a singularity. There's no way to avoid this within general relativity. This was deeply unsettling. The theory itself predicted places where it broke down. Then in 1974, Hawking made another discovery that shocked physics. He revealed that black holes are not completely black. They emit radiation. Hawking radiation, coming from the combination of general relativity with quantum mechanics. Empty space is not really empty. It is filled with quantum fluctuations, pairs of particles and antiparticles appearing for brief moments before annihilating each other. Normally, these pairs disappear too quickly to have any observable effect. But near the event horizon of a black hole, the point of no return, where escaping would require traveling faster than light, if a pair appears right at the edge, the particle inside can be pulled in before it annihilates with its partner, and the one outside escapes. To an outside observer, it looks like the black hole emitted a particle. The energy originated from the black hole. The particle that fell in slightly reduces its mass. The black hole gradually loses mass, it's slowly evaporating. The smaller the black hole, the faster it evaporates, since the temperature of the radiation is inversely proportional to its mass. A black hole with the mass of the Sun would take about 10 to the power of 67 years to evaporate, which is incomprehensibly more than the universe's age of 13.8 billion years. One the size of a mountain would evaporate in a fraction of a second in an explosion of extremely high-energy radiation. This was revolutionary. Black holes are not eternal, and it created a problem that has haunted physics for 50 years. The information paradox. Imagine throwing a book into a black hole. From the outside, you can only observe its mass, spin, and electric charge. There's nothing to distinguish what fell inside, whether it's a book, a rock, or a star. In the 1970s, John Wheeler summed this up by saying that black holes have no hair. If they were eternal, the information would remain locked inside, inaccessible but not destroyed. But Hawking radiation changes that. The black hole evaporates completely, turning into a cloud of thermal, random radiation, carrying no information about what created it, like the heat from a campfire, from which you can't tell what was burned. This would violate unitarity, the principle of quantum mechanics that says information is never truly lost, it just gets scrambled. Before we go deeper into the mystery, pause for a moment and notice something. This idea that no one fully understands, this theory that breaks down its singularities and might even destroy information, is something you use every day without realizing it. General relativity isn't just an abstract theory for black holes and the Big Bang. It affects your life in a very concrete way. Take the most obvious example, GPS. Your phone uses satellites about 20,000 kilometers up, transmitting the exact time according to atomic clocks on board. The device calculates your position by the time difference between signals from at least 4 satellites. But the clocks on the satellites don't tick at the same rate as the clocks on the ground. They move at about 14,000 kilometers per hour, and due to special relativity, this slows the clocks by about 7 microseconds per day. But they're also farther from the Earth's center of mass, experiencing weaker gravity. And according to general relativity, this speeds up the clocks by about 45 microseconds per day. On balance, they run about 38 microseconds faster per day. It may seem like a small amount, but without correction, your position would be off by about 11 kilometers each day. In just a few hours, GPS would become useless. The engineers program the clocks at a slightly different rate, compensating for relativity. Every time you use GPS, you're relying on Einstein's equations, and it works perfectly. But no one really understands what space-time actually is. We only know how to calculate its effects. Another example, even stranger, gold. It's the only yellow metal. Silver is silver-colored, copper is reddish, iron is gray. Why? Gold atoms are heavy, with 79 protons, creating a strong electric field that makes the innermost electrons move fast, enough for relativistic effects to come into play, increasing their effective mass and changing the spacing between energy levels. This shifts the absorption of light from ultraviolet to blue, and the reflected light ends up yellow. Without special relativity, gold would look silver, like almost every other metal. The same mechanism explains why mercury is the only metal that's liquid at room temperature. The inner electrons, with 80 protons pulling on them, move so fast that the bonds between mercury atoms become weaker, So Mercury melts at a much lower temperature than you would expect. And there's more. Part of the internet itself depends on this. Fiber optic cables carry pulses of light with extremely precise timing. And for communications where microseconds matter, like financial transactions, engineers need to correct for gravitational time dilation between cables at different altitudes. And there's LIGO, the Laser Interferometer Gravitational Wave Observatory, designed to detect ripples in spacetime caused by violent cosmic events. The effect is tiny. A gravitational wave can change the distance between 2 points separated by 4 kilometers by less than a 10,000th of the width of a proton. It's worth making a side note here because this story goes back decades with a name you might recognize. In 1957, at a conference in Chapel Hill, the first scientific meeting dedicated to general relativity, many physicists still doubted whether gravitational waves actually carried energy. Richard Feynman, under the pseudonym Mr. Smith, settled the discussion with a thought experiment. 2 beads sliding with friction on a rigid rod, perpendicular to the wave. If the wave passes, it stretches and compresses the distance between the beads, making them rub against the rod and generate heat. What this proves, argued Feynman, is that the wave did work on the system and therefore truly carries energy. The sticky bead argument convinced the skeptics almost 60 years before LIGO confirmed in practice exactly what Feynman had demonstrated with a rod and 2 imaginary beads. LIGO detects waves by splitting a laser beam into 2 perpendicular 4-kilometer tunnels, reflecting it off mirrors, and recombining the beams. A passing wave stretches one arm and compresses the other, creating a revealing interference pattern. The first detection happened on September 14, 2015. The signal lasted about 1/5 of a second, rising from 35 to 250 hertz, exactly the expected pattern of 2 black holes, 30 times the mass of the sun, spiraling until they merge and release even more energy in the merger. In a fraction of a second, more than all the stars in the observable universe emit in the same interval. The event happened 1.3 billion light-years away, and the discovery was announced on February 11, 2016, confirming a prediction that had never been directly tested before. In 2017, the Nobel Committee recognized this achievement. Rainer Weiss, Kip Thorne, and Barry Barish shared the Nobel Prize in Physics that year for building LIGO and for the detection of gravitational waves. A project that took more than 40 years from the initial idea to the result. A fun fact, the chair that Kip Thorne held at Caltech is officially called the Richard P. Feynman Professor of Theoretical Physics, named in honor of the same physicist who, 60 years earlier, had convinced the scientific community with 2 calculations and an imaginary stick that those waves really existed. Since 2015, LIGO and its sister observatories Virgo and Cagra have detected dozens of events. Most of them are black hole mergers, revealing a previously mysterious and intermediate mass population, as well as neutron star mergers. In August 2017, they detected 2 neutron stars merging 130 million light-years away. It was a special event because it also produced light, an explosion called a kilonova, observed by telescopes around the world at the birth of multi-messenger astronomy. The observations confirm that heavy elements like gold, platinum, and uranium are forged precisely in these collisions. All the gold on Earth, every ring, every coin, every bar in a bank vault, was born in a neutron star merger, billions of years before the solar system existed. And then came the photographs of black holes. In April 2019, the Event Horizon Telescope collaboration released the first image of a black hole, combining radio telescopes from Hawaii to Antarctica as if it were a single Earth-sized telescope. The result? A ring of light around a dark circle at the center of the Messier 87 galaxy, 55 million light-years away, with about 6.5 billion solar masses. What you see there is not the black hole itself, it's its effect on the surrounding spacetime. the light from the hot gas bent in focus by the extreme curvature. In May 2022, the image of Sagittarius A star came out, the black hole at the center of our own galaxy, with about 4 million solar masses. The same object that Genzel and Guez tracked orbit by orbit for decades in the work that earned them a share of the 2020 Nobel Prize, alongside Penrose. You use this idea every day, in GPS, in the color of gold, in the liquidity of mercury, in fiber optic networks, in gravitational wave detectors, in photographs of black holes. Humanity has built entire technologies on top of Einstein's framework, and that's both beautiful and unsettling. It's like discovering that your house is built on an invisible foundation. You can measure how it responds to weight, calculate how it bends under stress, predict how it will behave, but the material itself remains unknown. I can't tell you if that makes me feel more at ease or more uneasy. I think it's both at the same time. So come with me all the way into the mystery. What exactly is still not understood about spacetime? The answer isn't simple, but it comes down to three big questions. Three places where human knowledge hits a wall. I confess that this question is the one that keeps me up at night the most. What is spacetime? What is it made of? Einstein's equations describe how spacetime curves in response to mass and energy, but they don't say what it really is. In his theory, space and time are a smooth, infinitely divisible continuum. It works perfectly at the scales we observe, but there's reason to suspect that's not the whole story. Quantum mechanics says that almost everything in nature comes in discrete packets. Energy comes in quanta, light comes in photons, even the spin of the electron comes in discrete values. This suggests that space and time might also be quantized at the smallest possible length. The Planck length, about 10 to the minus 35 meters. If you enlarged a proton to the size of the observable universe, the Planck length would be the size of a tree. At this scale, the smooth fabric of space-time should break down into what physicists call quantum foam, turbulent and bubbling with fluctuations all the time. It's not possible to probe this scale directly. You would need an accelerator about 10 quadrillion times more powerful than the Large Hadron Collider. We're left with theory and indirect reasoning, with competing ideas, none of which can be tested directly. Loop quantum gravity says that space-time is woven from tiny loops connected in a network, with quantized area and volume, suggesting that singularities might not even really exist, replaced by a minimum volume. String theory says that the fundamental objects are not point particles, but strings vibrating in 10 or 11 dimensions, of which we only perceive 4 with the others curled up at scales close to the Planck length. It's elegant. It naturally includes gravity and unifies all the forces, but it has a serious problem. There are maybe 10 to the 500 possible versions, depending on how the extra dimensions are curled up. That's much more than the number of atoms in the observable universe, and the theory makes virtually no testable predictions at the energies we can reach. There's also a more radical idea. Maybe space-time is emergent, arising from something that doesn't even look like space or time. That's the intuition behind what's called ER equals EPR, named after Einstein-Rosen bridges and Einstein-Podolsky-Rosen correlations. In 1935, Einstein and his colleagues described quantum entanglement, two particles connected in such a way that measuring one instantly affects the other, no matter the distance. And Einstein and Nathan Rosen wrote about solutions in general relativity that contain wormholes, shortcuts through space-time, but they're too unstable for anything to pass through. Physicists have been wondering if there's a connection between the two phenomena. Maybe when two particles are entangled, they're linked through a tiny wormhole, and space-time itself would be woven from entanglement, a useful illusion describing something more fundamental. It's speculative, but it points to a fascinating possibility. Space and time might be emergent, just like the temperature and pressure of a gas emerge from the movement of individual molecules. What happened at the Big Bang? Running the expansion of the universe backwards with Einstein's equations, we inevitably arrive at a singularity. Infinite density, infinite temperature, infinite curvature. where the math stops working. That means we actually don't know what happened at the beginning. There is solid evidence for the Big Bang in a general sense. The universe is expanding. Galaxies are moving away in all directions, with their light red shifted, and the farther away they are, the faster they're moving away. This relationship, discovered by Adam Hubble in 1929, means that if you turn the clock back, everything gets closer together, up to a point. About 13.8 billion years ago, when the universe was incredibly hot and dense, that's what we call the Big Bang. Although it wasn't an explosion within space, but rather an expansion of space itself. There is another crucial piece of evidence, and I actually find it almost funny because it's so unlikely. In 1964, Arno Penzias and Robert Wilson discovered the cosmic microwave background radiation at Bell Labs in New Jersey, using an antenna built for satellite communication. They kept picking up background noise no matter where they pointed. They even suspected pigeon droppings on the antenna, until they discovered that physicists from Princeton, just a few kilometers away, had already predicted exactly that signal. If the universe had started out hot and dense, there should be leftover radiation from that phase, stretched by the expansion until it became uniform microwaves coming from all directions. In 1978, this accidental discovery earned Penzias and Wilson the Nobel Prize in Physics. A reminder that sometimes the most important discovery in someone's career is exactly the noise they've spent months trying to eliminate. This radiation is light left over from when the universe was only 380,000 years old. The temperature dropped below 3,000 Kelvin. Electrons and protons combined into neutral hydrogen, and light could suddenly travel freely. This radiation is detected today at 2.725 Kelvin, almost uniform, but with variations of 1 part in 100,000. The seeds of all structure in the universe. Since slightly denser regions attracted more matter over billions of years, becoming the galaxies we see today. Satellites like COBE, WMAP, and Planck mapped this and made it possible to calculate the age of the universe. Its composition, about 5% normal matter, 27% dark matter, 68% dark energy, and its geometry apparently flat. But in the very first moments, we run into problems. At Planck time, about 10 to the minus 43 seconds after the Big Bang, general relativity can no longer be trusted. We would need a quantum theory of gravity, which we don't have. The best patch is cosmic inflation, proposed in the early 1980s by Alan Guth. In a tiny instant, space expanded by a factor of at least 10 to the 26th power, explaining why the universe appears uniform and flat. But inflation doesn't solve the singularity problem, it just pushes it further back. Some alternatives propose that the universe bounced from a previous contraction or emerged from nothing through a quantum process. All speculative. It's like a map that shows the way, but has a blank spot at the destination. Written, "Here be dragons." Do black holes erase information? Quantum mechanics says that information is never truly lost. It may get scrambled, but it's always there, in principle, under a principle called unitarity. But Hawking radiation, being thermal and random, seems to violate that. If you threw a book into a black hole and waited for it to evaporate completely, you wouldn't be able to reconstruct the book from the resulting radiation. The information would have simply disappeared. For decades, physicists debated this in the so-called black hole war. The key insight came from the holographic principle. All the information about the inside of a black hole would be encoded on the event horizon. The area of this horizon, not its volume, is proportional to its entropy, which is strange since for ordinary objects, entropy is proportional to volume. This idea was extended. All the information in a volume of space could be encoded on the boundary of that volume, the universe as a hologram. String theory offers some support through the ADS-CFT correspondence. CFT, one of the most important discoveries in theoretical physics in the last 30 years, suggesting that gravity and space-time may emerge from a more fundamental quantum theory, which doesn't even include space and time as basic ingredients. but it was still necessary to explain how information escapes from the black hole. In 2019 and 2020, a series of papers introduced the concept of islands. When calculating the entropy of Hawking radiation, it's necessary to include a region inside the black hole itself, which is correlated with the escaping radiation. As it evaporates, this island grows until it includes the entire interior, and the radiation starts to carry all the information that fell inside. This mathematically solved an old puzzle, the Page curve, calculated in the 1990s by Dom Page. If information is conserved, the entropy of the radiation should first rise and then fall back to zero, exactly the curve that the island calculation reproduces. Most physicists think we're very close to solving the paradox, and this progress points to something profound. Space, time, and gravity might not be fundamental. They might emerge from quantum entanglement. And why does that matter? Because physics today relies on two major theories, general relativity and quantum mechanics, each extraordinarily successful in its own field, but they contradict each other when applied to the same situation: the interior of a black hole or the Big Bang. A quantum theory of gravity would unite the two pillars of physics, and history suggests that great unifications lead to technological revolutions. Maxwell, by unifying electricity and magnetism, led to radio and telecommunications. Quantum mechanics led to semiconductors and computers. Relativity, which once seemed abstract, now underpins GPS and explains the equivalence between mass and energy behind nuclear energy. No one knows what technologies a quantum theory of gravity could bring. More importantly, understanding space-time would answer questions that people have been asking for millennia. Where did the universe come from? What happens inside a black hole? Why does time flow in only one direction? There is something philosophically profound in the fact that space-time might not be fundamental. It's similar to the fact that we already know the solidity of matter is an emergent illusion. The atoms that make up a table are mostly empty space, and the sensation of solidity comes from electromagnetic forces between them. If space-time is emergent in the same way, distance and duration might be similar illusions. At the deepest level, maybe there is only quantum information, and space and time emerge from the pattern of these correlations. This raises fascinating questions about time travel. Einstein's equations actually allow solutions with closed time-like curves, paths that loop back to their own starting point in time. But these solutions create paradoxes, like the classic grandfather paradox. Stephen Hawking proposed the chronology protection conjecture, the idea that the very laws of physics prevent closed time-like curves from forming. No one knows which idea is correct, but the fact that the equations allow these solutions suggests that space-time is stranger than we imagine. Understanding space-time would also change what we expect for the future of civilization. If shortcuts through it are possible, entire galaxies could be connected. If not, each civilization would be confined to its own star system. And finally, there is the simple beauty of understanding. The mystery of space-time is one of the last great frontiers, the place where our two best theories collide, the gateway to understanding the beginning of the universe, the fate of matter inside a black hole, and perhaps the very nature of reality itself. I confess that, after spending too much time reading about this, I started looking at my own cell phone's GPS differently. It's no longer just a blue dot on the map. It's proof, working right in my pocket, that space and time bend, and that no one knows exactly why. I started feeling less of a need to have a ready answer for everything, and more curiosity to live right inside a question that's still open. Are you living through a rare moment without even realizing it? This is the first generation in history with tools capable of seriously investigating these questions. Detectors measuring ripples in space-time, telescopes photographing black holes, accelerators recreating conditions similar to those of the newborn universe. The answer could be just around the corner or centuries away. Science doesn't follow a schedule, but the simple fact that these questions are still being seriously asked after more than 100 years already says something. So come back with me to the beginning. Space-time. Einstein's idea has been tested thousands of times without ever failing, used every day in GPS satellites, in the technology around you, and yet the underlying mystery is still there. No one knows what it's made of. No one knows if it's fundamental or emergent. No one knows what happened at the Big Bang, where the equations predict a singularity in which physics simply stops working. No one fully understands whether black holes preserve information or destroy it, although the answer seems closer than ever. There are equations that describe its behavior, but a complete theory that explains its real nature is still missing. And I don't think that's a failure. I think that's exactly where physics is at, on the frontier. At the point where Einstein's smooth spacetime meets the quantum world, which is grainy and uncertain, the physicists working on this today are on the edge of a cliff, looking into the unknown, building bridges with mathematics, creativity, and centuries of accumulated knowledge. Many of these bridges will fail, but one of them might reach the other side, and when it does, it changes everything. So, the next time you use GPS or look at a photograph of a black hole or think about the Big Bang, remember this. You are facing one of the deepest mysteries in all of science, evidence of something you use every day, but don't truly understand. Space-time is real. You can measure it, photograph it, and detect waves moving through it, but nobody knows what it is. And that's okay. That's where the adventure begins. That's where science actually happens. Not in the answers already found, but in the questions that are still open. Einstein came up with this idea of space-time more than 100 years ago. It revolutionized physics, explained gravity, predicted black holes, gravitational waves, and the expansion of the universe. But Einstein himself would probably be the first to admit that it's not the end of the story. It's a step along the way. Beautiful, elegant, powerful, but still just a step. The final answer is waiting out there, in mathematics, in experiments, in observations yet to be made. Someone will find it, maybe even in this generation, maybe centuries from now. And when someone finds it, they'll look back to this moment when space-time was known to exist, but it still wasn't known what it was. And they'll see this as the turning point, the moment right before everything changed. And remember, the universe is full of mysteries waiting to be solved. Space-time is just one of them, but maybe it's the most important one.